Hello everyone, welcome to our presentation. This is Jiachun Zhang. We're honored to be here presenting our work, Continuous GNSS-RTK aided by LiDAR inertial odometry with intelligent GNSS selection in urban canyons. Other authors are Dr. Wen, Mr. Huang, Dr. Chen, and Dr. Xu. The report expands from the following aspects. In the first part, I'm going to begin with background. As we all know, accurate and globally referenced positioning is a key prerequisite for fully successful autonomous systems. However, under urban canyons, the performance of GNSS-RTK suffers from notorious multipath and NLOS. The great challenge is how to guarantee the accuracy of GNSS-RTK in urban canyons. Many papers work on sensor fusion to overcome the challenge, considering the complementariness of global sensors and local sensors. To be specific, GNSS-RTK provides global position in open areas, while as local sensors, LiDAR produces 3D point cloud map and 6D relative pose estimation. MU could provide high-frequency 6D eagle motion estimation. Lee's work in 2018 proposed tightly coupled integration of the single-frequency multi-GNSS-RTK and low-cost IMU via outlier-resistant ambiguity resolution and common filter strategy. The fixing rate improved by about 10%. However, residual-based outlier rejection suffers lack of permanence, and the performance relies heavily on the cost of the IMU sensor for long GNSS outage durations. Chang's work in 2019 performed direct fusion of GNSS-IN's LiDAR via window-based graph optimization. The positioning accuracy improved compared with GNSS-IN's integration and cartographer. However, the degraded GNSS-RTK solutions distort the accuracy of LiDAR MU odometry. Then the key point is how to select the available GNSS-RTK positioning measurements before its integration with the LiDAR and MU. Our previous work, coarse-to-fine loosely coupled LiDAR inertial odometry for urban positioning and mapping, achieve high accuracy relative pose estimation and 3D point cloud map in urban canyons. Of course, the estimation is local and suffers drift. Inspired by the outstanding capability of the environmental description of 3D LiDAR, we propose to employ the generated 3D point cloud map to evaluate the degree of urbanization or further GNSS-RTK selection. The overview of the proposed method is as follows. There are three candle inputs: LiDAR range measurements, IMU eagle motion measurements, and GNSS-RTK position measurements. Via the integration of LiDAR and IMU implemented in our previous work, LCLLO, a locally accurate 6D motion estimation and a registered point cloud map are continuously generated. With the assistance of the registered 3D point cloud map, the available GNSS-RTK selection module discard unavailable GNSS-RTK and preserve available GNSS-RTK position measurements. For backward corrected integration with posts from LCLLO, the continuous 60 globally optimized pose estimation is finally achieved. Let's focus on the available GNSS-RTK selection module intuitively as shown in our previous work. Large sky value indicates high-rise buildings around or obstruction overhead. The GNSS-RTK solution are more likely to be unavailable. While, on the contrary, small sky mask value indicates open area. The GNSS-RTK solution are more likely to be available. We finish the available GNSS-RTK selection by 3 steps. At first, for each input GNSS-RTK, we find its corresponding LiDAR frame according to the timestamp, which is synchronized by ROS. Secondly, acquire backward and forward surrounding point clouds from registered LiDAR frames around according to predefined range parameters. Ground points and singular points are removed for efficiency and numerical stability. This is an example of point cloud acquired according to the proposed method. At the last step, sky mask value is calculated. 360 degrees, that is 360 directions around the operating U-blocks GRK is considered. Take any direction DI as an example. All the possible elevation angles at DI are denoted as EDI1, EDI2, etc. is calculated via arctangent of registered point coordinates provided by LCLIO. The maximum angles of them is the final elevation angle EDI at the direction DI. Take all the directions into account. The final elevation angle of GRK is the mean of elevation angles at all directions. Next, let's focus on the backward-corrected integration progress. The back graph of optimization is as shown here. The states and measurements used in FGO is defined under one of these 3 coordinate frames: LiDAR body frame, LiDAR wheel frame, and the local ENU frame. The transformation matrix between the local ENU frame and the LiDAR wheel frame were pre-calibrated. The states to be estimated are 60 poses at LiDAR timestamps, with each of them expressed as a compound vector of translation and coordinate. The measurements input to construct vectors are 60 pose estimation from LCLL and 2D available GNSS-RTK position measurements. The objective function could be defined as follows. There are 2 kinds of factors. The first one is LCLL pose estimation factor depicted in green. The residual are defined as the relative pose error. The other one is GNSS-RTK position factor depicted in gray. The residuals are defined as the absolute 2D translation error. Now let's focus on the experimental results. The sensor setup as shown in the picture. U-Block's F9P receiver provides GNSS-RTK measurements. The Velodyne HDL32E 3D LiDAR collected 3D point clouds at 10 Hz. The XSMTI-10MU acquired acceleration and angular velocity at 200 Hz. The normalized band capture provides reference, that is ground truth. The results are quantitatively evaluated by absolute pose error implemented in EVO. The methods were validated on our previous published data of the Navy Hong Kong data 2019 40428. Two pipelines are compared. The first one is a conventional method, which loosely fills all the received GNSS-RTK with LCL-LO. The other one is a proposed method, which loosely fills selected GNSS-RTK with LCL-LO. The sky mask value results are plotted in the figure. In most cases, large sky mask value are accompanied by large APE as we expected, such as the first place. Pedestry overpass ahead and high-rise buildings on both sides, resulting large sky mask value and per position measurements with large APE. Small sky mask value are accompanied by small APE, such as the second place. At the open intersection, small sky mask value and position measurements with small APE are achieved. However, there is anomaly. At the third place, an open intersection, the position measurements are relatively good with small APE, while the street lights above the car detected by LiDAR resulting in large sky mask value. Next, let's look at the qualitative comparison results, which shows the trajectory with error mapped on. GLF loosely fills all the received GNSS-RTK with LCL-LO produces the first tragic trajectory. GLI 35 dig and GLI 15 dig fuses GNSS-RTK with sky mask value less than 35 dig and 15 dig respectively with LCL-LO. The trajectory was significantly more smooth. The quantitative comparison of the three methods are as follows. The RMSE of the translation part of APE of GLI 15 dig is improved by 80% compared by that of GLI 4. It's concluded that this paper proposes an intelligent available GNSS-RTK selection method exploiting the register 3D point map produced by LiDAR ML integrated state estimation pipeline. This paper developed selective GNSS-RTK LiDAR ML integration pipeline based on loosely coupled FGO to achieve continuous GNSS-RTK positioning in urban canyons. Verification of the sky mask evaluation, a method for intelligent available GNSS-RTK selection, is performed. Quantitative and qualitative comparison of the developed pipelines and the conventional pipelines is performed. The RMSE of APE is confirmed to be improved by 80%. For further study, we would like to implement adaptive threshold and robustness improvement for available GNSS-RTK selection and implement effective outlier rejection via GNSS-RTK measurements analysis and verification on more benchmarks. Thank you for your attention. If you have any questions or inquiries, please feel free to contact me.